Okay, so in this video we're going to keep our conversation going about pressure, right? But what we're going to look at is what happens when we vary pressures with depth in a fluid, right? So human bodies actually have this principle, or you experience this principle in a couple ways. One is when your ears pop, right? When you go, on a plane and you go up into the atmosphere. Okay. Another one is if you've ached, if you've gone in a deep dive in a pool and like your body just seems like it aches, right? Because you're getting this pressure on you. Okay. Now what happens is at the Earth's surface, the air pressure, right, exerted on you is a result of the weight of the air above you, right? So if I'm here on the surface of the Earth, think about that there's this column of air that is pushing down on me, right? And so that's where the pressure comes from. So now this pressure is reduced as you climb up in altitude because the weight of that air above you decreases, right? And so if I climb up a mountain, that's me climbing up a mountain, right? The column of air has shrunk, right? So my pressure at, if you want to say sea level, is going to be a lot greater than my pressure at if I went up to Denver, right? Which is a mile up. All right. Now, the effect is opposite with underwater. So underwater, not under. So underwater, the pressure exerted on you increases with increasing depth, right? So if I'm underwater, here I am swimming, right? The deeper I go, the more pressure I feel. And why is that? Because I've got more water above me, right? And so that's the way you can think about that, right? And so to determine the pressure at any depth in a fluid, you're just going to do rho GH, where rho is the density of the fluid, and H is the depth below the fluid surface, or the height of the column above you, right? So whatever you want to call it, it's just going to go from situation to situation. Okay, again, if it's water, it's going to be 1,000 kilograms per cubic meter. If it's air, it's going to be 1.29 kilograms times kilograms per cubic meter, right? And so they're going to have to distinguish what the fluid is. Now, one interesting to note is that if I have water at 1 meter in a bathtub or in a lake, it's going to actually have the same pressure, right? As long as I take the same water, put it down a depth of 1 meter, right, or take the pressure at 1 meter, I'm going to get the same amount of pressure, right? Because it's completely independent on where it's located. It's only dependent on that depth. Okay. So now a dam is 500 meters wide and the water is 80 meters deep at the dam. What does the average pressure on the dam do to the water? And they calculate the force exerted against the dam, right? And so what we're going to do is we're going to find the average pressure. And so we got to change up the equation just a little bit. Okay. So we're going to say average pressure is equal to density times rho GH, where now this is going to be the average height or average depth, which in this case will be 40 meters, right? Because essentially the average is in the middle. Okay, so we're going to do 1,000 times 9.81 times 40, and so it's going to tell me that it has a pressure of 3.92 times 10 to the 5th pascals. And now I can equate that to to determine the force, right? So force is PA, right? Pressure times area. And so the pressure is 0.92 times 10 to the fifth. The area is going to be 500 meters, right? Again, here's my dam, right? And here's my water. And so I have a depth of 80 meters. And this area that's hitting is 500 square meters. Oh, sorry, it's not 500 square meters, but it's 500 meters wide. So my area is going to be a rectangle, a 500 by 80 rectangle, right? And so how much force is being exerted on that? 1.57 times 10 to the 10th newtons. And if you just chop off this to make the 10 and 9, that's how many kilograms. Like, that's essentially the equivalent kilograms that would give you the same effect. So this is really looking at, a liquid. Now what happens when you look at air, right? And so now it goes from just being a pressure to being atmospheric pressure. So atmospheric pressure is another example of pressure due to the weight of a fluid. In this case, due to the weight of air above a given height. Okay. Now the average pressure at sea level is given by that standard air pressure. Now if you remember in chemistry, you may have talked about like STP. That just means standard temperature and pressure. In fact, this is not air, this should be atmospheric pressure, okay, ATM, where 1 ATM is 1.01 times 10 to the fifth pascals, or 101.3 kilopascals. Okay, so these are just conversion factors for atmospheric pressure. And so in this example, we're talking about calculate the average density of the atmosphere if it extends to an altitude of 120 kilometers. So we're just going to use that same equation. Pressure equals rho GH. This equation, understand, doesn't care if it's a liquid or if it's a gas. It just cares that you're looking for, a pressure at a height or with a given height. And so I'm looking for the density. So I'm going to do pressure over GH, right? And so it has the atmospheric pressure, 1.01 times 10 to the fifth pascals, divided by 9.81. Now I need to convert that 120 kilometers to meters. I'm just going to multiply it by 1,000, or put times 10 to the 3 after it. And the average density of the atmosphere, 0.0858 kilograms per cubic meter. Alright, and so here this says calculate the depth below the surface of water of which the pressure due to the weight of the water equals 1 atmosphere. So essentially we're doing a similar calculation, but we're changing out. Now we're looking at like how far in water do you have to be down to equal 1 atmosphere. So we're going to use the same equation, and now we're going to solve it for H. So we're going to do pressure equals rho G. And so we're going to do 1.01 times 10 to the fifth pascals divided by 1,000, because now we're in water, times 9.81. And you'll see it's considerably less, right? It's only 10.3 meters, how far you have to be. So essentially to get this, right, this pressure, you only have to go down 10 meters, where, look, you have to have 120 kilometers above you to get that same effect. Okay? So the next video we're going to look at is just a relationship that was established by Pascal and helps in modern technology centered around hydraulic lifts and so forth.